Hey everyone, in this video we're going to go over section 3.10, linear approximations and differentials. So, what we've seen so far, let me draw this real quick. For some function f, the value of the derivative of f is equal to the slope of this tangent line. This will be f prime of x. We'll call that one f of x. And we'll talk about specifically at this point A, which would make this point f of A. And so we can see for values very close to A, somewhere in this small open interval, the value of the derivative of f, or the y value we get from this line, is very close to the value we get from the function itself. So in this section what we're going to do is we're going to use the idea that the derivative is very similar to the function when we are in a very close neighborhood around A. Or we're going to approximate the values of f using just the derivative itself. So we're going to be using, like I said, this line to approximate values from this function. So we need the equation for this line. Well, the equation of the line that goes to the point A, f of A, is y minus f of A is equal to, we're going to get the slope from the derivative, f prime of A times x minus A. I'm going to move the y over, I'm going to move the f of A over and get y is equal to f prime of A times x minus A plus f of A. And we can think of this as a function. We'll actually call it a capital L of x. L for the linearization of this function. That's equal to f prime of A times x minus A plus f of A. And now this, which is just the equation of this line, will give us approximate values for this function, especially when we're really close to A. You can see if we choose a value over here, well, the value of the derivative, or the value of this function, is going to be quite a bit away from the value of this function. But if we pick a point somewhere over here, you can see that these two values are very close to each other. So this really shines when some values of f of x are difficult or even impossible to compute, and then you can approximate their values with the derivative. The important thing, and we'll use this at some point, is that this f of x, this one that we're trying to get information about, f of x, is approximately equal to the linearization. F prime of A times x minus A plus f of A. They are approximately equal, and the closer you are to A, the more accurate this approximation is. Yeah, we call this the linear approximation. Let me write this up. We call L of x the linear approximation. We got the linear approximation. We can also call it the tangent line approximation. Tangent line approximation, or linearization of f at A. So this line is either a linear approximation, a tangent line approximation, or the linearization. All three different words that mean the same thing. They all say that we're going to take this function, we're going to get the slope of its tangent line, we're going to come up with the equation of the line with that slope going through that point, and then we're going to use this line to approximate values of that function. So let's move on to example 1. What example 1 wants us to do is find the linearization of f of x is equal to the square root of x plus 3 at a is equal to 1, and use it to approximate the numbers the square root of 3.98 and the square root of 4.05. And then we'll talk about if these are going to be overestimations or underestimations for their true value. Let me cap that. Okay, so the first thing we want to do is we want to find the linearization of that function at that point, or when a is equal to 1. The linearization is just a fancy way of asking for the slope of the tangent line that goes through the point a, f of a. So that is f prime of a, x minus a, plus f of a. Well, we've got f of x, and I'm going to rewrite it instead of having a square root as having an exponent of 1/2. We'll need an f prime of x. That's going to be equal to 1/2 of x plus 3 to the negative 1/2 times the derivative of the inside, which is just 1. And we'll need f prime of 1. So f prime of 1 is equal to 1/2 of 1 plus 3 to the negative 1/2, which we can call 1/2 of 1 over the square root of 4, which is equal to 1/2 times 1/2, which is 1/4. So we've got our slope. F prime of 1 is equal to 1/4. And we need an f of a. F of a is 1. F of 1 is equal to the square root of 1 plus 3. Square root of 4 is equal to 2. So we've got our points. We've got our pieces. We've got our f of a, we've got our f prime of a, and we have a. The linearization of this function is equal to 1/4 of x minus 1 plus 2. Or we can call this 1/4 of x minus 1/4 plus 2, or L of x is equal to 1/4 of an x plus 7/4. So this is the linearization of that function, or this is the equation of the tangent line that goes through the point 1, 2, or a, f of a. But now, the thing to remember is that L of x is approximately equal to f of x, this f of x up here. So let's approximate some values. So the square root of 3.98, well, that's the same as the square root of 0.98 plus 3, which, if you look, is of this form. F of is equal to something square rooted plus 3. 0.98. 0.98. Okay. Now, f of x is about the same as L of x. So this is approximately equal to, now we go up here, 1/4 of our x value is 0.98 plus 7/4, which I have written down over here to be 1.995. The idea of this exercise, or the idea of this example, is that this number is a lot easier to compute than this number. We can actually compute this number by hand. You can do this division and you can add 7/4 to it. Doing square roots by hand is a little bit more difficult. So the idea is to simplify calculations. Now in the year 2020, when we have computers in our pockets that are capable of doing these, where does this actually get used? This typically will get used for finding zeros of a function. If you have some function, you can use this idea to try and figure out an x value of where the function crosses 0. That's an application. I wanted to share that with you because a lot of students they go, why do I need this? And I go, it gets used in this application a lot. We're just developing the skills needed to use in this application through these exercises. We've got to do 4.05, so let's do that too. So the square root of 4.05, well, that's the same thing as the square root of 1.05 plus 3. I keep on writing some number plus 3 because that's the function we were given. F of x is equal to some number plus 3. So we see that f of 1.05 is equal to the square root of 1.05 plus 3. We know f of 1.05 is about the same as L of 1.05, and I'm running out of horizontal space, so I'm going to start moving vertically, which is equal to 1/4 of 1.05 plus 7/4, which is equal to, and you'll have to excuse me, that's equal to 2.0125. So notice how we're really close to 4. That's what we care about. I'm sorry, yeah, we're really close to 4 for our square root. The further away we get, the less accurate this is. Without going through all the detail, let's just draw these things. So here is our square root function. And so what we have done is we have came up with the equation for the line at a specific point, at the point 1, 2. And I'll call this 1, 2. And the line looks something like this. So notice how our tangent line is above the function. Our tangent line is going to return an overestimate for all values of this function. And in fact, the further away from the point 1, 2 that we get, the larger our error becomes. So because the tangent line was above our function, we know we were going to have an overestimate. For example, if we had, let's say, 1/x, which looks something like that. Now for 1/x, it's going to depend. Over here where we have x being bigger than 0, our tangent line is always going to be beneath the function. So we'll have under estimates over here. But when we have x being less than 0, our tangent line is going to be above the function, and we'll have over estimates over there. How big your error term can be, we'll actually deal with that in the next example. There's no preset notion of how big an error can be. The industry that you're working in, the problems that you're working on, that will ultimately dictate how much error you can allow in your system. But Overall, the idea is, we call this thing the linearization. All it is the same thing we've been doing off and on throughout this semester, is we're finding the equation of the tangent line to that function at this point. Now what we're doing is we're using that line. We're saying, okay, what if this value is difficult to calculate? Well, this value is much easier to calculate because we calculate it based off a line, and lines are easy to work with, and that gap is small. That error is something we can live with. For all practical purposes, it's negligible. We don't care about that error. It doesn't affect our measurements. We are approximating values. So slope of tangent line, or we have equation of tangent line through a point, and now we're using that equation to approximate values of a function. So for example 2, let's discuss what it would take to get some sort of bound on the error that we're generating. Importantly, let's find the values of x. Such that the square root of x plus 3 being approximately equal to 1/4 of an x plus 7/4 is accurate within 0.5. We'll also do 0.1 as well. So we want to get a bound on the accuracy of this, meaning that we want these two values to be no further apart than that number. Or what we want is 1/4 of an x plus 7/4 minus the square root of x plus 3. We want the distance between these two numbers to be less than 0.5. What it means to have our accuracy within 0.5. I want the distance between those two numbers to be less than 0.5. And remember, distance is always greater than or equal to 0, which is why we use absolute values. Okay, so what we want to do now is we're going to break apart these absolute values. We're going to turn this into a compound inequality. We can say that negative 0.5 is less than 1/4 of an x plus 7/4 minus the square root of x plus 3, which is less than 0.5. All we've done is traded in our absolute values for a bound on either end. Now, what we want to do is we actually want to solve for this middle term, this 1/4 of x plus 7/4, by adding the square root of x plus 3 to all three sides, to each, you don't really call them terms, to each portion of the compound inequality, plus the square root of x plus 3 plus the square root of x plus 3. So what we get is the square root of x plus 3 minus 0.5 is less than 1/4 of an x plus 7/4, which is less than the square root of x plus 3 plus 0.5. So what we want to do is we're going to graph all three of these functions, and we are going to see where they intersect. So quickly, I'm going to jump over to Desmos, but I don't want to jump back and forth. So through the same work, if we wanted our accuracy to be within 0.5, we would say 1/4 of x plus 7/4 minus the square root of x plus 3 less than 0.5, which we can 0.1, which we break up our compound inequality. Negative 0.1 less than 1/4 of an x plus 7/4 minus the square root of x plus 3 less than 0.1. We add our original function. We don't add our linear approximation, we add our original function everywhere. To get the square root of x plus 3 minus 0.1 less than 1/4 of x plus 7/4, which has to be less than the square root of x plus 3 plus 0.1. So over in Desmos land, when we skip to 0.1, these are going to be the three functions I will have graphed to. I just wanted to show you the steps for both of them. So I'll be right back.
Okay, so here we are. In blue we have g of x is equal to the square root of x plus 0.5. In red we have the square root of x plus 3 minus 0.5. And in green we have our linearization of the function, the square root of x plus 3. And so when we graph these, what we care about is we care about these points of intersection. So let's see, and I have them both put in. We have these vertical lines at x is equal to 8.657, and over here at x is equal to negative 2.657. What these two numbers represent, and I wonder if I can't highlight, but what these two x values represent is the range of values in x in which our estimation is accurate to 0.5. So we graphed all three of our functions, and we're caring about the points of intersection. Notice how we never intersect this lower bound. We know, and from what I told you before, that that our linearization is always an overestimate. And in fact, we can see that if I put in a j of x, which is equal to the square root of x plus 3. So, and then I'll make that a different color. We'll go with purple. So you can see that our linearization, this green line, is always above the curve that we are approximating. So that's why our linearization always gives overestimations, because this tangent line is above the curve that we're approximating. Which, since it always gives overestimations, it makes sense, and I've turned off too many things, that at no point do we risk running into our lower bound. If we're going to make an error, we're going to get further away in the positive direction. For different functions, for functions that kind of, for lack of better terms, wiggle more, you have to be cautious of intersecting both your lower bound and your upper bound. Coincidentally, for this function, it worked out that we were only experiencing an overestimation. Similarly, yet different, if we go over here, and I actually can click that button. This is the same thing, but now if you look over here on the left, you can see that we're dealing with accuracy to 0.1. So we could zoom in, and we're going to have a tighter bound. We're going to have a more narrow window. We are going to have more of a restricted domain in order to stay within that level of accuracy. Remember that tangent lines, the closer you are to the point of the derivative, the more accurate your approximation is. Said the other way, the further away from that point of approximation you get, the less accurate your model is overall. But this is what we're doing when the book tells you to find bounds, find some sort of bounds, figure out values of x that make your model accurate to a certain value. This is one way to go about doing it. I would recommend you use some sort of graphing calculator. It's 2020. I don't know how many people really still use graphing calculators like they used to. Desmos is cool. Google is all right. There's other free things online that'll graph and give you this information. But for the most part, you're graphing, and then you're using some sort of computer-aided software to give you bounds on the value of x. You don't necessarily have to use computer-aided software. You can look at your values of x and go, oh, for this example, accuracy to 0.1, if I get further away than -1, or if I get further away than 3.5, I know I'm starting to get into kind of some troubled areas. So you don't necessarily need to know accuracy to that many decimal points. You can just get an idea. But that's the idea of what we're doing here for bounds on accuracy.
So this idea gets used pretty freely in physics and doesn't get explained too terribly often, but you'll see in physics papers that they'll say the sine of theta is approximately equal to theta, and the cosine of theta is approximately equal to 1, and this is when theta is near 0. So let's explore these two ideas. So both of them are going to come from the linearization. But without going into too much detail, here we have, to the best of my ability, the sine of theta. And now, if we explore what happens, or if we explore the line tangent to sine of theta near theta is equal to 0, we get this line. Now, the slope of the tangent line is approximately 1 at this location, because we know the derivative of sine is cosine, and cosine's value at 0 is 1. So we get that really close to theta being equal to 0, the slope of this line is about equal to 1. And also sine of theta is approximately 0 when we get really close to 0. So using that information, we get the linearization of x being equal to the slope of the tangent line, which is about 1, times x minus 0, because we're taking the slope at 0, plus sine of 0, which is about 0. Or we get the linearization of x is approximately equal to x, which is another way of saying sine of theta is about equal to theta when theta is near 0. It's also a natural question to ask, how near is near? And unfortunately, there is no good answer for that. How near, like I discussed before, is based off of how accurate you need your model to be, and what you're doing, what you're actually doing this for will ultimately dictate that. The book will tell you how near you need to be for the sake of doing your homework, but the industry in which you work will ultimately dictate how accurate you need your model to be. So sine of theta is approximately equal to theta. Similarly, cosine kind of looks like that. And as we get closer to 0, the slope of that tangent line is approximately 0. Approximately 0. And the value of cosine is about 1. So the linearization for cosine is going to be the slope of the tangent line, which is 0, x minus 0 plus 1, or L of x is equal to 1. So you'll see this get used freely in a lot of physics papers. If you ever experience the derivation of the wave equation, which I suspect you will in a differential equations class, they're going to use these results freely. They come from the linearization of the sine and cosine function. So the idea of linear approximations are sometimes formulated into the terminology and notation of differentials. So if we have some function y being equal to f of x, where f is a differentiable function, then the differential dx can be thought of an independent variable, and the differential dy will be defined in terms of dx. And in fact, we'll get that dy is equal to f prime of x times dx. And then, so what does this mean? Well, let's rewrite this equation. If we divide both sides by dx dy, if we divide both sides by dx, we'd get dy over dx is equal to f prime of x. Perfect. This is something we should know. We know that this is the slope of tangent line. That's supposed to be line, not time. So, the slope of the tangent line. Or we can think of it as, what is the slope? Well, a slope is just a rise divided by a run. That's all a slope is. So what this is telling us is that our change in y is equal to our slope times our change in x. Or, going back to these terms, our rise is equal to our rise divided by our run divided by our run. So this is the overall idea of these differentials. And I'm going to draw a picture of it here in a second. But you'll often see dy is equal to f prime of x times dx. And remember that f prime of x is just a slope. Dx is our change in x. You can think of it as a run. And what we're saying is, so based off of this approximation, based off of this slope, our approximate y value is going to be equal to our change in x times our slope. So let me get resituated and I'll draw you a picture of what all this means. So here's our picture of what I just said. So the thing is, dx and delta x, this is our change in x values. The reason why dx is equal to delta x is we're free to pick our values of x. We can pick any value of x to evaluate this function at. So we can always choose our x values. They are our independent variables. But now what we have is this dy. What dy is saying, okay, given this change in x values, if I use the derivative, I will get this amount of rise. So dy is the rise of the tangent line associated with this length of run. Dy is rise or fall. In this example, it's a rise, but there's nothing wrong with me flipping the picture upside down. Dy is rise/fall of tangent line, where delta y is the actual change in y. Because if we have some function, we can calculate this change in y going from this point P to this point Q. That would just be delta y. But the rise or fall of the tangent line, that'll give us the change in y coordinates from R down to P. So really this is the difference. We've got dy's and we've got delta y's floating around. A delta y is specifically the change in y, where y is equal to f of x. Dy, well, that's equal to our slope, f prime of x, times some amount of x, some change in x. So largely, and that's what I want to leave you at. These two notations, they get interchanged a lot. They do have different meanings. So in example 3, we'll see how dy and delta y can be different. Let's say we had some function y as a function of x, which is which is x cubed plus x squared minus 2x plus 1. So we have this function, and what we want to do is we want to compare the values of delta y and dy as x changes from, and the first thing we'll do as x changes from, I've lost it in my notes, 2 to 2.05, and the second one as x changes from 2 to 2.1. So this is going to be our setup. So delta y, and then for 1, we'll do delta y, because delta y is just equal to the change in y values, and we can get the change in y values. And I'll say exact y values. So delta y is going to be equal to f of 2.05 minus f of 2. And looking off camera, that's going to be equal to, oh, I lost it, 9.717625 minus 9 is equal to 0.717625. So what this value represents is how much the function actually changed as x went from 2 to 2.05. But now for b, or for our other part, when we calculate dy, dy is equal to f prime of x times delta x. Well, we can calculate what f prime of y is. That says dy is equal to 3x squared plus 2x minus 2 times dx. And now what we want to do is we want to calculate the change in delta and dy of this function from this point. So we get dy is equal to 3 times 2 squared plus 2 times 2 minus 2, because remember we're using the slope at the point 2 times our change in x. Well, as we're going from 2 to 2.05, our change in x is going to be 0.05. So what this works out is actually going to be 0.7 when you crunch out the numbers on a calculator or blindly trust what the book has given you. So you can see these values are different, and that should make sense. After all, we are able to calculate the exact change in y, the exact change in y being delta y. And what we're doing is, for some functions, now this function is easy to find values for, some functions it might be difficult or impossible to find values. What we're doing is we're using this idea of a differential to approximate the value of a function at a new point. And as we can see, we are underestimating in this function. For the second one, we'll do 2. I'm going to have to look back. We're doing 2 over to 2.1. So our change in y, our exact change in y, delta y, is going to be equal to f of 2.1 minus f of 2. And looking off screen, that's equal to 9.140701 minus f of 2 is still 9, which is 0.140701. Perfect. Now, when we actually want to calculate dy, well, that's f prime of x dx, or dy is equal to, we take the derivative, which was 3x squared plus 2x minus 2 times our change in x. We're going to evaluate this slope at our starting point. What do I mean by a starting point? Well, we're starting somewhere and we're letting x vary to another number. So we evaluate the derivative at the starting point. dy is going to be equal to 3 times 2 squared plus 2 times 2 minus 2 times how far we drift. Well, we're going from 2.0 to 2.1, so that's going to be 0.1. Crunching all that into a calculator, that gives us 0.14. So once again, we can approximate the change in y. These examples really are geared to showing you that this approximation is a good approximation for this value, given some assumptions that the book takes care of for you. But really, this is something we have been doing. The big new thing is right down here, and it boils down to this formula. dy is equal to f prime of x dx. You got to calculate f prime of x. And then we have to evaluate it somewhere. We're taking, everything is based off of this initial point. Like in this example, this would be 2 and this would be 2.1. What we're doing is we're calculating, we know exactly what dx is. Dx is just how big of a step we take. And now, in order to get the slope of this tangent line, we need the derivative of the function evaluated at that point, at this start point, at kind of this beginning spot. Once we have the derivative, and you could get this number kind of off screen and then treat it just like a number and substitute it back in. But that's our idea. We're using this idea of a differential to approximate y values, and look, these approximations can be very good under certain conditions. So for our final example, example 4. So the radius of a sphere was measured and found to be 21 centimeters. So radius of sphere was measured to be 21 centimeters with a possible error with the possible error in measurement of at most 0.05 centimeters. What is the maximum? What is the maximum error in the volume? How did they say it? What is the maximum error using this value of the radius? What is the maximum error using this value of the radius to compute the volume of the sphere? Perfect. So what we have is we have this sphere. We've measured the radius and we have some error, and we want to know how much that error is going to impact the overall volume. Well, we know that the volume of a sphere is going to be equal to 4/3 pi r cubed. So, using the differential, we can take the derivative of both sides, and we get the change in volume is equal to 4/3 pi. I'm taking the derivative of r, which is 3r squared. This 3 in the denominator, we'll cancel out with that 3, and we're left with our change in volume is equal to 4 pi r squared. Perfect. So, I'm sorry, dr. dr. We need the derivative there. Apologize. We got a dv over here, got a dr over there. So now we want to know how much the volume can actually change. We want to figure out what dv is. Well, dv is going to be equal to 4 pi. Now our radius is going to be 21 squared times our change in r, 0.05. And when you crunch all these numbers together, you get dv being about equal to 277 centimeters cubed, which might seem like a lot. That does seem like a very large error, but when we compare it to the actual error, when we compare it to the actual volume, this is when the error itself isn't necessarily as important as the relative error. What is the relative error? Well, the relative error, in less words than more, is what you got divided by what it was. So for this problem, the relative error, which I'm just going to call RE. I don't believe the book calls it RE, but I'm trying to not run out of space. What we got? Well, what we got was governed by the formula 4 pi r squared dr. And what the value actually was governed by the formula 4/3 pi r cubed. Now we know all of these values, and through simplifying, this would actually become 3 dr over r, which approximately equals 0.007. So our relative error is 0.007. So number, our percent error is our relative error as a percent. So for this problem, our percent error was 0.7%. So 270 centimeters cubed might be a large amount of volume, but given the volume of this sphere, it actually isn't that much. So a lot of times, just a raw number, I want these to be within a certain value like we did, I believe in example 2, is less useful than coming up with this percent error on your bound. Because after all, you want your error to be a small percentage of what you measure. That concludes this section. We're taking derivatives and we're using that derivative to approximate the function. This gets used a lot if we have some sort of, and let me draw it this way. If we have some surface, and at the point we can take a derivative, and we haven't done calculus in higher dimensions yet, but you can imagine we have some wavy surface, like maybe a coral reef, and if we have the derivative of a function, we get a line. If we take the derivative of a surface, we can get a tangential surface. You guys will be doing this in Calc 3. But where this idea really gets used is people will not be able to come up with an exact equation that models this surface, but they can measure changes in certain parameters. And based off the change in certain parameters, they can gain information about a surface that they care about. What we're doing right now is calculus in one dimension, so we're doing linear approximations. In higher dimensions, where this gets used more, we're talking about tangent planes to surfaces. Nothing like this on your homework, but I like to let you know why. Speaking of homework, go off and do 1 through 17 odd. Do 23 through 27, and do 35. This is already up on Blackboard with the appropriate due date. Send me a question, or send me an email if you guys have any questions, and I'll talk to you next time. Bye-bye.